Starting recording. Okay, so I did want to make one quick announcement. This is by no means gospel, but supposedly there will be a section of stochastic OR that gets taught in the summer. So if you're in the situation where you're still on the waiting list and it doesn't look like you're going to get in, everything I've been told is they're trying to teach it in the summer, and that's their plan. And same thing with simulation. So just a heads up for those of you who are concerned about that. Okay, so last time we sort of started wrapping up about how do we discuss probability when we have multiple outcomes. We're actually not talking about how we calculate these quantities quite yet. We're just setting up the rules for probability, okay? And so in the end of last lecture, we started discussing how do we sort of break apart more complex events that are sort of built together by different outcomes. So I think in one case I was talking about what is the probability that my niece is born in June and she's born on a Monday, right? And so what we're talking about is the intersection, right? Or you can think of that as an and statement of, well, really it's the intersection because we're talking about the sets. The set of all days in June and the set of all days that are Monday. And when we find the intersection of those two, we're left with some specific dates. Okay. Based on these sets and the size of those sets, then we can calculate or we can make some sort of statement saying how we calculate or how we state what is the probability of event 1 and event 2 occurring. Now, if those two events are mutually exclusive, that is, they can't both happen at the same time, then when we're talking about the intersection of these two sets, that means there's no overlap, okay? And so the intersection of two sets that don't have any elements in common, so all the days in June are certainly completely separate from all the days in July, and they have no overlap. So when we take the intersection of these two sets, we get the null set. And again, that's spelled, N-U-L-L, the null set, okay, which is basically nothing. It's the set equivalent of 0 in some way. In that case, because there's nothing in the set, right, if we try to calculate, well, what's the probability of that actually happening, we're talking about the probability of nothing happening, right, so it just can't. And so the probability is always going to be equal to 0. Okay? And so this will happen in some cases. Now, perhaps the more interesting case is when we have two events, or more useful, are two events that are independent. Right? And what we mean by that is the probability of one event does not affect the probability of another event. Okay? So maybe a better example of this might be, let's say, my niece is born on a Monday, and event 2 might be my niece has brown eyes. Okay. Logically, I hope we can understand that these two events have nothing to do with each other. Okay? And so if we want to calculate what's the probability of my niece being born on Monday and having brown eyes, then we can just apply this equation here. And we say, well, the probability of both those things being true is just the probability of my niece being born on Monday and the probability of my niece having brown eyes. Okay? Event 1 does not affect event 2. And certainly the color of my niece's eyes does not affect the day that she's born on. All right. So in that sense, they're independent. Okay. Now, I do want to be a little bit careful about how I draw things here, because when we were talking about sample spaces before, what we did is, I draw some volume of space, and then I say, well, this is maybe, so this is our sample space. These are all the elements of that sample space corresponding to event 1, and then all the elements in event 2. Okay. I want to be careful here. So even though I'm drawing this sample space, so again, we could pretend this is my niece having brown eyes and being born on a Monday. The dimensions of this sample space are actually not like flat, right? So one way you might, maybe a better way of drawing this might be, so I don't know what all the different eye colors are. So black, brown, green, blue, what else is there? Gray, red. Actually, that does happen, right? Okay. And then in terms of days of the week, we have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, right? Yeah, something like that. Okay. So this might be a better way of organizing it. So if we're talking about, this whole box might be our sample space. And note, it's in 2 dimensions, right? The day dimension is independent of it's separate dimension from the color. And really what we're talking about is this block right here. Everything that's inside of here. Okay? But when we draw it using these simplified diagrams here, E1 and E2, understand that even though we draw them, like there's no axis here, right? You don't know what dimension corresponds to what. This is sort of like a hyperdimensional representation of what's going on in the world, okay? So just be careful about dividing these 2 things in your space, in your head, and making sure when you see me draw these things, this is sort of a notional representation, okay? And in fact, our sample space is 2-dimensional, okay? 1 dimension of the sample space is the eye color, and the other dimension is the day of the week, okay? Let's say I were to add another sample space, which might be hair color, right? So again, we'd have black, brown, well, no green hair. What other? Red, blonde. Okay. That would add a 3rd dimension. Okay? And if we were to draw the sample space of being born on a Monday and having brown hair, then what we'd effectively do is extend this box through all the different hair colors, right? But if you were to ask me to draw this like I normally do, right, I would draw it like this. I'd go, ooh, doo-doo-doo. E1 is day of the week, E2 is eye color, and then E3 is hair color. Okay? So we should understand that these diagrams, again, are notional, right? I have to flatten the 3D world out, and it just sort of represents, so if we were to talk about all of the people, well, yeah. So event 1 is born on Monday. Let's say event 2 is, what was it, brown eyes? Yeah. And let's say event 3, we could make it blonde hair. All right, that sample space is found at the intersection of these 3 different sets. Okay? But this is a hyperdimensional set, right? It's 3 dimensions here. We have day of the week, eye color, hair color, making 3 axes, but when I draw it, I'm always going to draw it sort of flat. So just keep that in mind. I know sometimes it sort of presents some confusions. Okay. Okay. Yeah. All right. So after we figure out ands, so let's say, again, if we wanted to calculate what's the probability of E1 and E2, and actually I'm just going to keep it like that. And assuming these events are independent, then we can just multiply their probabilities. Now, there's no reason why E2 can't itself be a complex event. Okay? Let's say E2 was equal to E3 and E4. Okay, so again, this might be, actually, we'll just make it arbitrary. It doesn't really matter. Okay, so really what we're talking about here is sometimes we'll have cases, so we could have PE1 and E2, but really what we're talking about is E1 and E3 and E4. All right. Assuming E1 is independent of E2, we can still apply this law or this rule. So we just say that this quantity is equal to E1 times the probability of E3 and E4. Okay. And if E3 and E4 break apart or are independent, then we can multiply their probabilities times each other. Okay. And so this is kind of recursive, right? As long as they're independent, then we can always multiply them. So more generally, if we're given EI corresponding to event I with a total of n independent events, then the probability of E1 and E2 and E3 ... and En is just equal to the multiplication of 1 to n times the probability of EI. Okay? So if you haven't seen this symbol before, it's basically instead of summing a whole bunch of numbers, it's just multiplying a whole bunch of numbers together. Same idea. This term right here, there's a nice way to represent the sum of or the intersection of a bunch of stuffs. We could have written this as the probability of the intersection of I equals 1 to n of E of I. So this is just some shorthand notation to make life a little bit easier. Okay? So if you have a bunch of independent events, you can just multiply their probabilities times each other, assuming that you know them. All right. So that's how we deal with and events. Okay, so the next basic operation that we're going to use in set theory and probability is an or statement. All right. So a lot of times we're going to ask ourselves, what's the probability of event 1 happening or event 2 happening? Right? And this could be something as, what's the probability of my niece being born on a Monday or a Tuesday? Okay. Or it could be, again, these don't even have to be in the same dimension. Right? So day of the week might be a dimension, so Monday and Tuesday. It could be, what's the probability of my niece having brown eyes or being born on a Monday? Perfectly logical statement. Or semantically logical. I don't know why you would ask it, but you could. Right? Okay, now, I mentioned before that the book uses a little bit different notation. All right. So before, I think I told you that the probability of A and B is just written as the probability of A times B. And that kind of makes sense because if they're independent, you would just multiply them. Okay? All right. The book keeps up with this sort of notation of using multiplying for and. For or, it uses plus or addition. Okay? So the book, you'll see the book talk about the probability of E1 plus E2. Okay? So don't be confused if you see that. This is just how the book writes it. Okay, and really what they're saying is, what's the probability of E1 happening or E2 happening? Yes, sir.
With an or statement, does it mean it can only be one of the things happening, or can both things happen?
Both things could happen, or one of them could happen. Yeah. All right. And so there's a law that sort of tells us how we can go ahead and calculate this. All right. So there's the law, the addition law of probability. And this is kind of why the book uses this plus notation. It sort of makes some sense. So if you have events E1 and E2, it doesn't matter whether they're independent or dependent on each other. This equation will always work. Then it's just given by the probability of E1 happening plus the probability of E2 happening minus the probability of E1 and E2. Right. So if we want to think of this pictorially, I'm sure some of you guys remember this from probability. We draw sort of like our Venn diagrams. This is our sample space. Okay, here goes our set E1 and our set of events E2. What we're doing is we're adding up the probability that's inside of E1. Then we're adding up the probability inside of E2. Okay. But the problem is we double counted this middle part. So we need to subtract that middle part, right? Because we double counted it. So if we subtract one, we're left with just adding it once. Okay. And so that's what we end up seeing here. This probability E1 corresponds to the blue area. Oops. This probability E2 corresponds to the red area. And then what we're doing here is just subtracting off the double counting that happens when we add those probabilities. Okay. So there are some simplifications. You don't need to memorize these necessarily, but they make life a lot easier if you do. So let's say E1 and E2 are mutually exclusive. And again, remember, mutually exclusive means they both can't happen at the same time. Okay, you can't be born in June and July. It's one or the other. Okay. In that case, if we look at our equation, right, so we have E1 or E2, PE1 plus PE2, and then we have the intersection of E1 and E2. All right. We know this intersection has to be equal to 0. All right. They have nothing in common. You can't be born in June and July. And so what ends up happening is this probability is 0. And so if you ever have two sets that are mutually exclusive, then the probability of one or the other event occurring is just the sum of their probabilities. Okay. And notionally, the way that we draw this, so let's say we have our sample space. We have E1 here and E2 here. They don't overlap each other. Okay? So these are the days in June, these are the days in July. And so if we want to know the probability of being born in June or July, all we do is add up all the probability that's contained in here and all the probability that's contained in the E2 sort of region. Okay? So that makes life a little bit easier. And again, it comes from this idea that with mutually exclusive events, E1 and E2 is equal to the null set, which implies the probability of E1 and E2 is 0. Okay, so that makes life pretty easy. Certainly, if E1 and E2 are independent, we could make another simplification. All right. In that case, we still have our probability of E1 and or E2. So if we know they're independent, okay, so the day my niece was born is independent of her hair color, we can break apart this probability here. So that might make life easier if I've given you certain values or your problem comes with certain values. So you can calculate this quantity. Okay, so that makes life a little bit easier. Oh, fun. Okay. So I played roulette I went to some casino on New Year's. Have any of you guys ever played roulette? Very complicated for somebody who has no idea what's going on. But really, really fun. So I highly suggest, well, no, I don't want to encourage gambling. If you like probability and statistics, it's a really cool game to learn. Oh, no, not roulette. Roulette, actually, that is still a really good game to learn. Craps. Have you guys ever played craps? Does anybody know how to play?
Is it like the one with the dice?
Yeah, it's the one with the dice. Yeah. They always played in Bond movies and stuff. Yeah, so that one's actually really fun. I think supposedly that gives you the nearest odds to not losing in a casino. You'll always lose in a casino, but okay, but fun game. Very complicated. And it deals with dice, so that's always good for probability. All right, so I want to go through a couple quick problems. They're in the notes, but I think always, again, I know you guys can just read these notes if you wanted to, and you'd probably get 90% or 80% of what I'm talking about. But I think some of the nuance that I add in lecture is usually a little bit more useful, and you guys have the opportunity to interject with a quick question. Okay. So let's say we're playing craps and we got a pair of dice, okay? And we're going to assume that these dice are fair. Okay, so 2 6-sided die. They're both going to be fair. And so if we talk about what's the probability, and actually let's call this. So we're going to have, I might have to introduce some notation. All right. So I'm going to introduce some notation. We're going to talk about x1 and x2, and these are going to be random variables. Okay, and we're going to use these to construct some events. Okay. And so these random variables are going to represent what I roll on the first die and what I roll on the second die. Okay. Okay. So with these dies, because they're 6-sided, right, we know x1 can either be equal to 1, x1 can be equal to 2, right, all the way to x1 being equal to 6. Okay. And so each one of these cases corresponds to a simple event. Okay. So this simple event is, the first die we roll a 1. But we're going to go through, we should define the probabilities of all the possible outcomes because we're actually going to do some calculations. Okay. And so what we're going to assume is that we have fair die. So what's the probability of rolling the 1? 1, 6. All right, cool. Probability of rolling a 2? 1, 6. Probability of rolling a 6? 1, 6. All right. And this is going to be true for both die. All right. So if we want to write it a little bit more, mathy, we could say something like the probability of x1 is equal to I is equal to 1, 6 for all I in 1, 2, ... 6. Okay? So the probability of the first die being rolled to equal one of these numbers is 1, 6. This upside down A, for those of you who don't know, means for all. Okay. So the probability that x1, the first roll is equal to 1 equals 1, 6. Probability x1 equals 2, 1, 6, 3, 1, 6, so forth. So there's just a little bit shorter notation instead of writing them all out. I'm giving you the equation on how to calculate the probability. Likewise, we can do the same thing for the second die that we're rolling. Yeah, cool. All right. So let's make some fun events. So let's say we have one event is going to be equal to the set where x1 plus x2 is even. And our second event is just going to be that x1 is greater than 5. Okay. So let's sort of think, let's take away the math. All I'm saying is I roll 2 die. What's the probability of those 2 die adding up to be even? All right. The second event is that the first die is either a 5 or a 6. Okay. So intuitively, if I have 2 die and I roll them, what's the probability I get an even number? 50%. This is the one exception to the 0 or 1 rule, right? 50%. Okay. So it's a 50% chance that my die roll is even. Okay. So just keep that in mind, and I think it ends up working a little bit later. E2 is the probability that I roll a 5 or a 6, and we should just think, well, the probability of rolling a 5 is 1, 6. The probability of rolling a 6 is 1, 6. So if we add those 2 up, the probability of rolling a 5 or 6 is what? 1/3. Okay. Good. So we already sort of know our answers. But now we're going to sort of go through the annoying math to sort of apply some rules. Okay? And so these should sort of serve as checks. And so we're going to calculate a few values. What's the probability of E1 occurring? What's the probability of E2 occurring? We'll do what's the probability of E1 and E2, and what's the probability of E1 or E2. All righty. So we're going to start with the probability that of E1. Okay, and again, this is we roll an even number. Okay. All right. So if we have 2 dies, how can we roll an even number?
Even plus an even or an odd plus an odd.
That's right. So we can either roll even, or an odd. All right. So one thing that we can do is we can deconstruct E1 into 2 options. All right. So the first one is x1 and x2. Well, actually, we'll just write it this way. x1 is odd. x2 is odd. So that's one way we can get an even number. Or the other way is x1 is even and x2 is even. Okay. And so these are two new sets that I've defined. Okay. The first set is where x1 and x2 are odd. It's the set of all the roles where that happens. And this second set are all the ways that x1 and x2 can be even. Okay. And so let's sort of think about, like, we could go through all the different roles. How many different roles are there? 36. Okay, I don't really want to go through them, but 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. All right, and we keep going down all of them until 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Okay? And so when we think about all the different ways we can get an even number, what we're talking about is that could happen, that could happen, that could happen, this could happen, this could happen, this could happen. And we go through and we sort of highlight all the different ways we can roll two even numbers. And what you should see is that these two sets independently make that up. Okay? So in one option, we have two odd numbers. Right? In the other option, we have two even numbers. And so the blue boxes, if you include all the red boxes, gives you all the green boxes. And so this is the same thing. All right, so just keep this in mind notionally. Okay. The next property that we can use here, and actually we can even, if you want to visualize what's going on, so here goes the set E1. Basically what I did is I divided it in two. So x1 is odd, x2 is odd, and then x1 is even, x2 is even. Okay. So you add two halves together, you get the whole back. Okay, so the next trick that we can use is this idea that let's assume that the roll of each dice is independent of each other. Right? They don't affect each other outcome. Okay. So x1 being odd is independent of x2 being odd. Okay. Oh, wait, no, that's not the roll we want to use quite yet. Ooh, we want to do something else. We want to break apart this OR statement. Sorry. Okay. So, again, let's sort of look at our old rule. So I'm just going to write it a little bit differently. Probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay? So we can apply that here because we have an OR statement. So what we're talking about is the probability x1 is odd and x2 is odd plus the probability x1 is even and x2 is even minus the probability x1 is odd and x2 is odd and x1 is even and x2 is even. Okay. Yes, sir.
I think. Okay, wait, no, never mind.
Yeah. All right. So the neat part about and statements, and the reason why, again, this, if you want to think back to why the book uses multiplication, if I were to say A times B, that's equal to B times A. Okay. And I could do A times B times C, and that's equal to C times B times A. All right. You can sort of mix things up. All right. It doesn't even matter if you have parentheses around them. Right. So I think this is a rule that you might have learned in math at one point. A times the quantity B times C is equal to A times B times C. Right, that quantity. And so the same thing happens with intersections, where it's kind of like a multiplication, and so we don't even need these parentheses, so we can sort of drop them. And we can write them in any order that we want. All right? So let's look at the statement. It is the probability that x1 is odd, something, and x1 is even. Is it possible for x1 to be both even and odd? No. Okay. Is it possible for x2 to be odd and even? Can x2 be odd and x2 be even? No. At the same time. Okay. So what is this set equal to? Set. The null set. Yeah. So this is the null set. The probability of the null set is 0. Yeah. So this whole thing's 0. Okay. So again, we already know the answer. This probability is 1/2, but we're going through all the annoying math to show that the probability of rolling an even number is equal to the probability that x1 is odd and x2 is odd plus the probability x1 is even and x2 is even. Okay. So now is when we use the idea of independent events. Okay. The first die and second die, let's assume the values that I roll, they're independent of each other. Okay. Excuse me. Because of independence, right? Whenever we have independence, if we have the probability of A and B, we can break apart their probabilities. Okay, and just multiply them. So that allows us to break apart this statement here and this statement here. Okay. So if we want, we can rewrite this as the probability that x1 is odd and x2 is odd is equal to the probability that x1 is odd times the probability that x2 is odd. Okay. And we're going to add to it the probability that x1 is even times the probability that x2 is even. Alrighty. Almost done. Alrighty. Alright, so I'm just going to do this once because I don't think I need to do it 4 different times. Let's think about this probability that x1 is odd. Okay. How many different ways can x1 be odd? 3. What are those different ways? 1, 3, and 5. Okay. If x... Actually, and let me ask another question. Are those mutually exclusive?
Yes.
Yes. So if I roll a 1, it can't be a 5 or a 3 at the same time. Okay? So the probability that x1 is odd, that's just equal to the probability that x1 is equal to 1, or x1 is equal to 2, or x1, oh, not 2, sorry, 3, or x1 is equal to 5. Okay. I know I'm being very overly pedantic here, but I just want to show all these rules. Okay. We can use this additive probability law and recognize that only one of these events can happen. And so when you do OR with independent events, all you have to do is add up their individual probabilities. So that's equal to the probability that x1 is equal to 1, plus the probability that x1 is equal to 3, plus the probability x1 is equal to 5. Okay, do we know these quantities?
Yes.
Yes. All right, so finally we got to a value that we actually know, that I told you from the very beginning. All right, all the way up here, I gave you these probabilities, okay? And our goal in applying these equations was to get to a point where we could actually calculate something. All right, so I know the probability of the first roll being a 1 is 1/6. The probability of x1 being 3 is 1/6. Plus the probability of x1 being 5 is 1/6. Okay? And so the probability that x1 is odd is just 1/6 plus 1/6 plus 1/6, which is 1/2. Okay. Now you can go through the same process for calculating what's the probability x2 is odd, or what the probability x1 is even, or what the probability x2 is even. Okay? And you get the same answer each time, which is 1/2. And so when we start filling stuff in, we get 1/2 times 1/2 plus 1/2 times 1/2. So 1/4 plus 1/4 gives us 1/2. Okay, so a lot of math for something we already knew the answer to. But the whole point was to show you how we can use this, the idea of mutually exclusive events when we're doing ORs and ANDs, right? What happens when we have independent events with OR and AND, okay? Using these laws, okay? But these are important probability properties that we need to use, okay? All right, we're not going to go through all the cases, but we'll do one more. Actually, do we want to do one more? We don't have time. Ooh. Yeah. Okay, so this is the probability, that I roll an odd number. Is it an odd number? No, even number. And, well, the second die is 5 or 6. Okay? So again, let's sort of write this down. Okay, so we can actually enumerate all the different ways that our roll can be even while our second die is 5 or 6. Okay, so if we have D1 and D2, if I roll a 5 for D1, if I roll a 5 for D2, what does D1 have to be in order for the total roll to be even? 1, 3, or 5. Okay. Or I could roll a 6 here. In that case, D1 has to be 2, 4, or 6. Okay? And so we know we have, again, we're sort of jumping ahead. We have 6 total ways that this can happen. There are 36 total ways to roll dice. All right? Each of these events has the same probability. Okay? And so what ends up happening is we should get a probability of what? 6 over 36. So that's probably what we're going to get. But we sort of made a few jumps and conclusions along the way. Okay. But we're going to calculate it from the very beginning. Okay. So let's sort of write this down a little bit differently. So as I said, sometimes I find it useful to write things out in words. So that first event corresponds to x1 plus x2 is even. All right. And x2 is 5 or 6. Okay. Oh, did I not teach you guys De Morgan's law yet? Did we go over De Morgan's? You did it. Okay. All right. I think we can still make this happen.
You're gonna go with base theorem too?
Yeah, that'll be next. Okay. So one thing that we can do here is actually partition this stuff up a little bit. Okay. So I'm going to erase this, but just keep it in your mind. Okay. So let this first circle represent x1 plus x2 is even. This next set here is going to correspond to x2 equals 5 or x2 equals 6. And in fact, we can divide that up. Right? So let's say this right-hand half is x2 equals 6, and this right-hand half is x2 equals 5. So really what we want to do is we want to add up all the probability that's inside of here and inside of here. Okay. Or we could think about it as one big circle. Okay. So we want to add up the probability that's inside of the green area. But we can see there's this sort of natural split between x2 equals 5 and x2 equals 6. Right? And that happens over here. So one way that we can rewrite this probability, is by saying, well, we can get x1 plus x2 is even when x2 is 5, or we can get x1 plus 2 being even when x2 is 6. So another way to write that is x1 plus x2 is even, and x2 is 5, or x1 plus x2 is even, and x2 is equal to 6. And so there's an application of another probability law. I'll probably, hopefully, introduce it very, very soon. But logically, hopefully, you can see where it makes some sense that these two red areas are the same thing as that green area. All right. Okay. Now let's think about these. This is one red area, right? So the guy on the left. And there's another red area, the guy on the right. Can we visually understand how these both can't happen at the same time?
Yes.
Because can x2 be 5 and x2 be 6 at the same time? No. Okay. So these have to be mutually exclusive events. All right. So they can't happen at the same time. And because of that, we can apply our probability law of unions. So let me write it again. So A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay? Now, A and B are mutually exclusive, so there's 0. And so all that we're left with is A and B. Okay? And again, okay. All right. So we can break up these probability into two different parts. Okay. So they're no longer in a single probability statement. They're broken up into two probability statements. Okay. Oh, I have it right there. Why didn't I say it? Yeah. Okay. So at this point, I think I do need to give that law I was telling you about. Okay. All right. So I should have just done it here. I'm sorry for not doing that. So sets have the distributive property. Okay, so normally we think of, in math, we think of A times B plus C is equal to A plus A times C, all right? You guys know this whenever you do like quadratics and stuff like that. So logic sort of works the same funny sort of way. All right. And so there's a few different distributive laws. The first one, okay, so this one sort of mirrors the one up above, right? So and is usually kind of thought of like multiplication, while or is addition, okay? And so if we apply the same thought process and we distribute our intersection, then we get A and B. Ooh, yeah. Or A and C. Okay. So that's one useful property. The other one is when you sort of mix up or use a different set of order of the and or. So here I'm saying, let's take B and C, right, and or it with A. So that ends up being the same thing as A or B, ending it with A or C. Does that actually follow the same logic if we were to do that here? Oh, not really. Ooh, no, it doesn't really work the same way there. But certainly that does. Okay. All right, so this is one of the rules that we actually applied when we did that split. Okay, and we're going to use it again. Yes, sir?
Does that only work whenever they're mutually exclusive, like in this example for x2?
No, this always works. Yeah. This always works. Yes, sir.
You called this De Morgan's law?
Sorry, it's not De Morgan's. It's actually distributive
It's
property.
just distributed?
Yeah, I didn't look up De Morgan's law. It might be De Morgan's. I always forget. I'm bad at remembering names. Oh, De Morgan's has to do with when you have a not statement. We'll get to that probably in next lecture, I think. Okay. All right, so I know this is getting a little bit messy, but nonetheless, we can apply probably what we need to. Okay. All right. So how can x1 and plus x2 be even? There are two ways that rolling dice can be even.
Odd plus odd
Yeah,
or even.
odd plus odd, even plus even. Okay, odd plus odd, even plus even. And so, in fact, that's going to form. So, if we want to think about it in terms of the distributive law, so B will be rolling two odds. C will be rolling two evens. While A will be something like x2 equals 5. Okay? Oops. So it's a little bit written backwards, but we got that there. Okay. And same thing for this bottom equation. x1 plus x2 is even, and x2 equals 6 is sort of the same thing as B or C here ANDed with A. Okay. And so this is our distributed law. Right. And so we can apply this law, and we can split it apart now. All right. And so what we want to do is sort of just get the probability of B times the probability of A, and with the probability of A, plus the probability associated with this bottom line. Okay, so how do we do that? Basically, what we end up with is, this is always weird for me. Okay. God, this hurts my brain. If this hurts my brain, this must be killing y'all.
Would it not be easier to do it the other way? To make
Wait, did I just do it that way? Oh, wait, we just did it that way. Oh, this is easy. Oh, okay. Sorry, got it. Man, we just applied to more. Okay. All right. If x2 is 5, all right, then what we're talking about, x1 has to be what? Odd. So let's sort of rewrite this. So, God, that was like way more of a logical jump than I think taken. All right, so we know in this case, x1 plus x2 is even, and x2 is 5. The only way for x1 and x2 to be even while x2 is 5 means x1 has to be even as well. So we're sort of using some deductive logic here. All right. Now let's look at the second case. If x2 is 6, in order for x1 and x2 to be even, what does x1 have to be? Even or odd? Even, yeah. Yeah, that took way more work than it should have. Okay. All right. So now we finally get to the point. Whatever happens to dice 1 has nothing to do with dice 2, so these are mutually independent. Independent. Right. Exclusive is when they both can't happen at the same time. So these are independent of each other. So that means we can break apart this and statement. Okay. So we'll say the probability x1 is odd times the probability that x2 is equal to 5 plus the probability x2 is even times the probability x2 is 6. All right. This probability we calculated about 5 or 10 minutes ago. What's the probability that x1 is odd? 1/2. What's the probability that I roll a 5? 1/6. What's the probability x2 is even? 1/2. What's the probability x2 is 6? 1/6. So we end up with 1/6. Yeah, you add these all up. 1/12 plus 1/12 is 2/12. 1/6. What did we say it would be in the beginning?
1/6.
1/6. Okay. Again, a lot of work for something that seems logical. Okay. The reason why I wanted to work through this is because at some point, the only piece of information we're given is the probability of x1 equals 1, probability of x1 equals 2, probability of x2 equals 3, and so forth. And so somehow we have to work through our math to get to that very base equation or those base quantities. Okay? Alrighty. I should start a new page. Okay. The last thing we're going to learn before we take off for the day, I think we end at 2:40?
45.
Oh, 2:45. Perfect. Okay. We're going to learn about the conditional law of probability. Okay. So the way this works is we're going to be given two events, E1 and E2. And we're just going to require the probability of E2 is greater than 0. So when we talk about conditional probability, we're basically saying, what is the probability that E1 happens given E2 is true? All right. So the equation for conditional probability is given by the probability of E1 and E2 happening divided by the probability of E2 happening. And so now we see why we require the probability of E2 to be greater than 0. At least mathematically, if it's 0, then this quantity doesn't make sense, the division. Okay. So what is this asking? What's the probability UCF wins the football game given we're leading at halftime? So this is typically how these statements will come about. So there are some useful properties that allow us to make some simplifications. Okay. So the first one is when E2 is a subset of E1. Okay, so what does that mean? So let's say there's our sample space. There's E1. All right. And then what we're saying is when we say E2 is a subset, that means E2 has to be fully contained within E1. Okay. So the example I always like to give is with animals. So let's say we're talking about pets. E2 is the probability that you own a dog. E1 is the probability that you own a mammal. Okay? All dogs are mammals. Okay? So E2 is a subset, dogs are a subset of mammals. They're fully contained within it. Okay? This allows us to make some simplifications. Okay, so if we go back to this equation, the probability of E1 given E2 is equal to the probability of E1 and E2 all over the probability of E2. Okay. So I'm kind of asking, what's the probability? So again, this is the sort of the example. I don't know how to spell mammal, but I'm just going to scribble something. M-A-M-M-A-L. Okay. So let me ask you guys a question. What's the probability your pet is a mammal if I tell you your pet is a dog? 100%, right? Okay, so we kind of know the answer of where we're going with this. All right. So I'll sort of work this. So the probability that it's a mammal and it's a dog. Does anybody know what this probability is equal to? No, it's not one. So what kind of pets are there in the world? We got mammals, reptiles, our fish. Oh, amphibians. There we go. That's a good one. All right. Avians aren't mammals, right?
No.
Yeah, they're their own thing. Okay. All right. So we know we have different types of I don't know genuses, or I don't know what those are called, right? And then within each one we have different types. Okay. So the question is, what is this probability? So let's think about it in terms of our sets. So this is mammal. This is dog. What is the area covered by mammal and dog? Where would I fill in?
All the mammals.
And dog, though. So this is all mammal. This is all dog. Where do those overlap?
The dog part.
Just in the dog part, right? So mammal and dog is just equal to dog. Okay? So we can think of this as the probability of dog. So if we know the probability of dog, then we're all set. Okay, so let's go back over here. Same idea. All right, but instead of mammals and dogs, we're just calling them E1 and E2. If E2 is a subset of E1, then the probability of E1 and E2 is just the probability of E2. Okay? And we're still left with the bottom, the probability of E2. So these are the same quantities, right? And they're both bigger than 0. So we just get 1. Okay, so this explains the probability of having a mammal given that you have a dog. Yeah, it's 1, right? That's pretty easy. So that's a neat little property. The example here. What's the probability of being born on a weekend given you're born on a Saturday?
Pretty good.
1. All right. Okay. There's one other useful property, which has to do with if E1 and E2 are independent from each other. All right, so let's sort of work out. So I'll give you the answer, but we can work it out. So the probability of E1 given E2, that's just going to be equal to the probability of E1. Okay, let's see where that comes from. So we know that the probability of E1 given E2 is equal to the probability of E1 and E2 all over the probability of E2. Okay? But the other piece of information that's given is that E1 and E2 are independent. So I can break apart this probability right there. So we have now the probability of E1 times the probability of E2 all over the probability of E2. Okay, we can cancel some stuff out. And we're left with the probability of E1. Okay. So what's well, not practical example of this. What is the probability that Adam has a dog given that I have a Samsung S9? Does it change? Does it matter? No. The probability of him having a dog has nothing to do with the type of phone I have. All right? These are two independent events. So it makes sense that the probability of Adam having a dog, it doesn't matter whether I have a Samsung or not. Okay? So this is actually quite a useful property. All right, we're going to learn one more. And this will get us to Adam's favorite Bayes' law at some point. This is the first step towards Bayes' law. Okay. So let's say we can talk about the probability of E1 given E2. And we can talk about the probability of E2 given E1. It's going to end up happening that sometimes you're given one piece of information but not the other. So I might give you this information but ask you to calculate that. Or I might give you this information, ask you to calculate that. Or it just might be easier to calculate one versus the other in some weird way. All right. But let's what we're going to do is we're going to link these two equations through a common term. All right. So this first equation is the probability of E1 and E2 all over the probability of E2. All right. The second equation, probability of E1 and E2 all over the probability of E1. Okay. Do these two equations have anything in common?
The numerators.
The numerators, right? They both have the probability of E1 and E2 in both their numerators. All right, so what I'm going to do is I'm actually going to solve for the probability of E1, E2. All right, so over here, we have the probability of E1 given E2 times the probability of E2. And on the bottom, we have the probability of E1 and E2 is equal to the probability of E2 given E1 times probability of E1. Okay. So all these quantities, we can now relate back to each other. All right. So the probability of E1 and E2 is equal to the probability of E1 given E2 times the probability of E2. And that's equal to the probability of E2 given E1 times the probability of E1. Okay? So there will be cases where I say, give me the probability of E1 and E2, and you have these two quantities. Or I might do something like, I don't know, I'll give you this quantity and that quantity, and somehow you have to find this third quantity. Okay? It all sorts of works out in different ways. This rule, this conditional probability rule, and what will later become Bayes' theorem, which is an extension of this, is the foundation of everything involving machine learning. Right? So if you guys have machine learning as like an interest of yours, then this is your new, like, one of your 10 commandments. Okay? I don't know which one, but it's up there. Because machine learning basically says, well, we could start from this one, right? What's a common? Okay, so let's say one algorithm, very important thing in finances. Given your credit score, what's the probability that you default on a car loan? Right? This is a very important machine learning problem. E1, or whatever, E2, doesn't really matter, is your credit score. What's the probability you default? Okay? And what happens is, though, a lot of times we get the information backwards. Right? We get a whole bunch of data of people who have defaulted and their credit scores, and we have to infer the other direction. And so we're actually given E1 given E2. And so what machine learning does is it basically flips the argument around to find the inference in the other direction. Okay, so given some data, what can we predict about what will happen? All right, with that, we're going to wrap up. Expect to see some homework coming out, hopefully today or tomorrow, from Valeria. It'll be short. Thank you, guys. Be careful. 1 second.